that we can bound isotropic constant of k by sigma n, which is on each side, it's its most root log n. So this would imply that we have section of root log n. Let me just comment that it is also true that for an isotropic log concave random vector the same holds. And also there is an equivalence. So if you can prove slicing problem for convex bodies and it follows from log concave measures, this is thanks to the work of Keith Ball from 80s, for at least in the central symmetric case, and I think in other papers, in my paper, it's in for the general case. Okay, so the way to prove this theorem is not exactly through Gaussian convolution, but through some very related concept. We're going to use a Laplace transform. Okay, so let's suppose that we are, okay, so for now we prove this theorem. So we start with some isotropic log concave random vector x in Rn. Okay, so it's logarithmic Laplace transform is what? So it's lambda, lambda of x at y, or just lambda at y. So it's the logarithm of the expectation of e to the x times y. Okay, so it's a modification of the Gaussian convolution that we saw earlier. We write omega for the set where it's finite. Okay, so it's really finite at 0. In fact, it is also finite at some neighborhood of 0 because x decays exponentially. So if you have exponentially notes for small y, the Laplace transform is finite. In fact, it is a convex and open set. In Rn. It could be all of Rn. It's pretty common. Why is it convex? By Cauchy-Schwarz, because if for y1 it's finite and for y2 is finite, then for the y1 plus y2 over 2, you do Cauchy-Schwarz, you get it convex. And why is it open? Because if it's finite for at some point, then you have some, you know that the integral of, sorry, the density is rho. As usual, the density is rho. So if it's finite at some point, then you know that this is integrable. But this is, again, log concave, so you get, again, a log concave measure of finite integral. So it decays exponentially at infinity, so you can move a little bit around it and show that it's open. Okay, so it is convex and open. And lambda on omega is smooth and convex. Smooth, you believe, I guess, and convex, again, by Cauchy-Schwarz or Helder. Maybe we should say Helder, not Cauchy-Schwarz. By Helder, you get that it's convex. Okay. Now, for computing derivatives of the log Laplace transform of lambda, it's good to introduce the tilts. We introduce tilts. So what is this tilt? The tilt is closely related to this Gaussian localized needle that we saw yesterday. So for y in omega, we look at, let's call it rho y or something. So rho y of x will be x to the xy rho of x over e to the lambda y. So let's see what's written here. So we tilt kind of, we put more weight. If rho is supported in some convex set, this is the direction of y, then we put more weight to this side of y, we get another low concave measure. This is low concave, clearly, because you just multiply by linear function, and we normalize to get a probability density. Okay, so this is basically a Gaussian needle, just without the Gaussian, the quadratic factor in the exponent. So it's, yeah, it's almost the same. And let's write also x sub y for the random vector with density rho y. Okay? And the claim so we may express derivatives of lambda with the help of this tilted random vector. This is because the Laplace transform is the cumulant degenerating function. We have some formulas for, sorry, the following lemma. We have some formula for the derivatives. So I need the first three derivatives. Okay, so the gradient of lambda is the barycenter of xy. Okay, let me call it ay. I think this was a tradition in both my and Joseph lectures. So this is one of the rare examples where we agreed on the notation, not S and sigma, but just saying. Okay, so that's the barycenter. Then the Hessian is the covariance matrix of xy. That's the second cumulant. And the third tensor, okay, third tensor is scary, but yeah, it's in R by N by N by N. So it's a box of numbers. Okay, so this thing is the third cumulant, which some of you might know that this is just the third moment tensor of this random vector xy. And this is just proven by differentiating. So this is the log Laplace transform. This is lambda of, just differentiate and see that you get these things. Okay, and we use such things already in the Gaussian case, and it's more or less the same. Another thing that we see is that for any y, so xy is a tilted random variable. In particular, it's absolutely continuous, so its covariance is no-negative definite. And this means, so I will not prove this lemma, I think it's clear. So this means that that lambda is strongly convex. This is how you call functions whose Hessian is positive definite. And if I look at the gradient map, so this is the gradient map, like Brenier's map. You can take a convex function, look at the gradient. This means that this is 1-to-1. Why is it 1-to-1? Because you know this thing. So if I have 2 points, x1 and x2, I claim that this is non-zero. Why this thing is non-zero? Because if I take the scalar product with x1 minus x2, if I take the scalar product, this is the integral of the Hessian along the line, and this would be non-zero. In fact, it will be positive because the gradient is increasing. This is the directional derivative of lambda along the line from x1 to x2. It's strictly increasing, so yeah, so it is 1-to-1. And this would be good for us, that you can change variable using this gradient of lambda. Okay, another thing that we would need is to look at determinants of covariance matrices. So we discussed the slicing problem. So we better look at the determinant of the covariance matrix, which appears in the isotropic constant. So we have lambda, which is Laplace transform. Any question? Anyone wants to say anything? No question, no remark? Okay, so we consider the determinant function. Oh, let me call it the tilde. Yeah, I like it. F of y on the domain of the Laplace transform. So it's log of the determinant of the Hessian of lambda, which is also the log of the determinant of the covariance of xy. So we have two functions. We have lambda, the Laplace transform. We have f, which is some determinant function. Okay? And now we have the following lemma. So the claim is that at any point y in omega, if I look at the inverse matrix to this Hessian, and I multiply by grad f and grad f, this is at most n sigma n square. Okay, it looks maybe at this point a bit strange, right? What's the relation? Why would you inverse this matrix? Yes? So maybe there is some interpretation to this lemma, and indeed we'll see that it has some meaning. We'll see it from the proof. Okay. So let me do the proof. Any questions? So proof. Okay, this is a bit of a strange lemma. Let's begin by checking one particular point, the 0 point. 0 is inside omega, we know, because it's a probability measure, it's finite mass. So let's check it first for y equals 0. Okay. So we need to look at the function which is log determinant and differentiate it. Yes? How do you differentiate log determinant? So let's just do the directional derivative in some direction. So for some vector in direction, some direction. What is the directional derivative of f at the origin in this direction? Okay, so we have our function f, and we just want to differentiate it this way. And this is log of a determinant of the Hessian of lambda. How do you differentiate log of a determinant? Some of us remember this is the trace of the inverse matrix times the derivative of the matrix itself. Right, this is how we differentiate logarithm of determinant. It's the trace of the inverse matrix times the change in the matrix. Okay. Now, this, as we said, is the covariance of xy, but just of x, because there's no tilt at the origin. So this is identity. Very good. And now, what is this matrix here? So we know that this is, we had a lemma to compute the third derivatives of the log Laplace transform. And we said that this will be the cumulant. So this is basically the, since x is centered, there's no tilt. X is x0. This would be something like, take a look at the third tensor of x times v. Or if you want, it is the trace of the expectation of xv. Right? What does it mean to take a tensor? This is a symmetric tensor, so if you to multiply it to a cap, how to say, they have a word in algebra. Take a tensor and contract. Thank you. They contract, they don't multiply. Okay, so we contract now for 1 second. We don't multiply by v, we contract with v. for some reason. So by contracting with V, this is symmetric tensor, so it's clear, there's no question in which entry to it will give you the same result. So after you multiply by V, I stop contraction. Okay. I multiply by V, so I get X times V, and then X, the third tensor, which is also, so what's the trace of the third tensor, which is X squared. Okay. And now, unfortunately, I don't use Bourgain-Minkowski, but I use Cauchy-Schwarz once again. So I get square root of xv, and I use the fancy Cauchy-Schwarz, which when you get the variance all the time. So yeah, and then this is 1, actually equals 1, because it's isotropic. So I get root of n sigma n, because this is at most n sigma n squared. By definition, it's called x2. Okay, so at least we got something. This is for fixed vector v. Since this is true for any unit vector v, we understand that grad f at 0 is at most root of n sigma n, or the Hessian minus 1, grad f square. Is that what a square? Yeah, no square. Ah, this is, oh, okay. So this is at most n sigma n. This equals grad f square, because this is identity. So this is at most n sigma n square. Okay, so we proved it just at one point. Okay. Now, how would you prove it in other points? So there are two possibilities. Either to make a computation which is only slightly longer than this one, or avoid computation and think invariantly about the situation. And this is what we will do. I'm not sure it will take less time, but maybe we'll understand why. I mean, this is true, and why would you come up with this, and why is it natural with these things. Okay, so we'll try not. Yes, please, Joseph. I did say.
This is all invariant, right? So lemma is a fine invariant.
Yes, but I think X is isotropic. I said. In the third board up, in the left.
But in the lemma, is X assumed to be X?
No need. Yeah, so throughout X, I assume this is a topic, but you're right that this lemma holds in greater generality. Yes, it holds without isotropicity at all. Okay, so why does it hold in greater generality? So the idea is that this expression that is written here is in fact the length of the squared length of a Riemannian gradient of f in some way. So we want to introduce some Riemannian structure. Okay, so we consider the following Riemannian structure, Riemannian metric. Which we call G on the space omega, which is actually the Hessian metric of lambda. So how would you define this Riemannian metric? So at y, if I have a point y in omega, and I have two tangent vectors v, and I mean it's Rn, so saying tangent is like saying just Rn. So I have two directions, u and v. What would be G at uv? Okay, so what is the length at the point y of these two vectors u and v? Well, I just take the Hessian of lambda at y, u times v. Okay, so this is a legitimate Riemannian metric because this is positive definite. So this is indeed a Riemannian metric on this space omega. Okay, now so this means that the length of, if you have the length of the unit vector u. So what is the length of u? This, when I put sub g, I mean with respect to the metric g. What is the length of g? It will be the square root of the Hessian of lambda u times u. Right? This is the meaning of, this is the length of the vector. It's the second derivative. The directional second derivative of lambda in the direction of u is the length. Okay. And now, what is the Riemannian gradient of f? So the Riemannian gradient and the length of the Riemannian gradient with respect to g. So gradient of a function is the supremum of all unit vectors of length 1 of the derivative of u, of the change in u, let's say of grad f times u, or if you want the directional derivative of f with respect to u. If I don't put a subscript, this is Euclidean stuff. Okay. What is it? So this is, well, I mean, this is supremum of that Hessian of lambda at y u is smaller than 1 of grad f dot u, which equals the inverse matrix. Okay, so what we need to prove is that basically that f is a Riemannian Lipschitz function, that the gradient is at most n sigma n square everywhere. So f is square root of n sigma n Lipschitz with respect to the Riemannian metric g, omega g. This is what we want to prove. Okay, now, so I said that we want to think in an invariant way. So okay. I think it's easy to remember these things, right? It's just the Hessian metric. Okay. So I want to think in an invariant way, so I want to reduce structures that I'm not using. So for example, I want to think about f only up to a constant. So let me say that when I write for a function, let's say little f, so f means that a function f up to a constant, if you want, or additive constant, or in other words, this is equivalence class. So it's equivalence class of the following relation. Of the relations that f is equivalent to g, if and only if f minus g is constant. Okay. Now, the structure that I'm thinking about now is the following. So let me remind you. So we have g at y of uv is the Hessian of lambda at y uv. And in addition to the Riemannian metric, I also want to add the function f. So I call it, I'm not sure it was a good name, but I call it the Riemannian package associated with x. Is a triplet of, first of all, the Riemannian metric. So omega is the manifold, G is the metric, and the equivalence class of f. Okay, so this I call mx. Okay, this is the triplet associated with the random vector x. Okay? And now, when would you say that two are isomorphic? When do two random variables x and y have isomorphic Riemannian packages? If there is an isometry, so Riemannian isometry between the two manifolds that transforms f also, that maps f correctly, properly. So correctly. So it maps the f of one of them to the f of the other. So this is when two things like that are isomorphic. I think this is also clear, okay? And now, let's, am I running too fast? Is questions about whatever I did so far? Okay. Now what happens to the Riemannian package under various operations? For example, if we translate x, if I replace x but x plus some fixed vector x naught, what happens to the package? I think nothing. So if I change x to x naught, okay, so translating x, so if I pass from x to x plus some fixed vector x0, so actually there is really nothing happens. So the isometry is just the identity map. Why? Because what happens to lambda when we translate x? So lambda is this thing. So if you translate x, you just get some linear function added, which means that in the Hessian you see nothing. So it's the same Riemannian metric. And also the determinant of the covariance, so really nothing happens. So translating gives you exactly the same package. So this package is invariant translations. Okay, so this, Joseph, you said also, okay, this is the next step, linear function, but also translations. Yes. Second thing, let's check tilts. So what happens if I replace x by the tilt x, y naught for some fixed vector y naught? So I claim that again, the packages are equivalent, but this time the isometry is not completely trivial. It's not identity. So the isomorphism is translation by y. By y naught. Translating by y naught. So you translate, the set omega, the metric G, everything you translate by y naught. Why is that? So what happens when you replace, this is lambda of x. What is lambda of x y naught? So it's log of exponential of e to the xy naught times y, which is log of the integral of e to the x0y times rho of x times e to the x times y dx over some normalizing factor. And you kind of see that these two things together add to y plus y naught. And so the Laplace transform just being translated. Maybe you get some additive constant, but since we took the equivalence class, you get exactly the same package. The package is isomorphic after you translate. And now, as Joseph said, if I apply a linear map, also nothing happens. Okay, so if I take linear map, so if I replace, if x goes to some t of x, then again, these are isomorphic, t is invertible. Then again, this is isomorphic, and the isomorphism is just I think the linear map in the dual space. That's because actually this is well defined whenever X is a random vector in some abstract linear space. It's a log concave random vector in abstract linear space, so you cannot possibly see anything linear. You cannot possibly see the linear structure. So this isotropistic could not be at all relevant in an n-dimensional linear space. Okay, so now without Euclidean structure even. Okay, so what do we get from these observations? So if I use the first bullet and the second one, so the first one and the third one tell me that what I wanted at 0 holds true for any, without isotopicity. This is smaller than n sigma n square. For any log concave random vector X with no phasor assumption. And if I use the second point with the tilts, this tilt invariance gives me that not only at 0, but 0 is not a special point. So you can translate. So this gives it for any y. Okay, so this proves this lemma. Okay, so we worked to prove this lemma, introduce this structure. Is it just a way to make the proof with less computations? Yes, a bit, but also you can now try to begin to study this Riemannian geometry, maybe in a more geometric way. So for example, what can we say about Riemannian balls? So lemma is that, so our standing assumption is X log concave and isotropic. This is, okay. The lemma is that for any R, if I look at the Riemannian ball of radius root of R, it contains the level set of the Laplace transform. Okay, so we have lambda, we have the level sets, and the ball is a bit larger. Okay, let's prove it. So we pick some y in this set, so it means that lambda of 2y is at most r. Okay, and I want to show that I can connect it. There is a path from 0 to y of length at most square root of r, and I'll just try the straight line segment. So take the line segment gamma of t be just t times y for t between 0 and 1. And let's compute the length of this segment. So what's the length of this curve? It is the integral between 0 to 1 of the length of the tangent vector. So I need to look at tangent vector at ty times gamma dot. Gamma dot is y. Okay, I want to get the square root outside, so I'll use Cauchy-Schwarz. In fact, I'll do it in a bit more, I get a factor. So I do it in this way. So I'm going to get from 0 to 1. Here I want to put 2 minus t for some reason. By the way, this thing here, it's the second derivative of lambda at the point ty. You know? So here I'll get the second derivative of lambda ty dt. And here will be the integral from 0 to 1 of 1 over 2 minus t dt. And let me even increase this integral from 1 to 2. And why do I do this? Because this...
With respect to t, it's in y, or the derivative, or the partial derivative of lambda.
It's the second derivative, directional derivative in the direction of y. We can keep this term if you prefer this way. Anyway, the reason why I wanted to work with this term, so this is the remainder in Taylor's formula. So this is with the integral. Everything here, this is the integral remainder in Taylor's theorem. So this just equals the value of lambda at ty minus the Taylor approximation. So lambda at naught, lambda at 0 plus, which is plus grad lambda at 0 times 2y. So this is exactly the remaining Taylor approximation. But so we have lambda of 0 equals 0 because x is log concave, because x is a random vector. Lambda of 0 is 0 for any random vector. And since x is centered, so here I only assume that x is centered, this will be also 0. Okay? So what I get is that this thing equals lambda of 2y. So this equals square root of lambda of 2y. Now I need to know this integral. If I want to write equal, logarithm of 2. Okay? So I got that the length of this curve is, let's say, at most root of lambda of ty, which is at most square root of r. Okay, so the length is indeed at most square root of r, as I said, so the ball is inside. Very good. Now we may prove the theorem, finally. Okay, so prove the theorem. Proof of Lk smaller than C sigma n. Okay, so there will be two steps that two little inequalities that I'll prove in a second. So one of them, we claim that the volume of K is at least e to the minus n times the volume of this ball, Riemannian ball. So we'll take R will be n over sigma n squared. Now we claim that this is at least the volume of this Riemannian ball, but this is a bit strange. So this is the Riemannian ball, but I take Euclidean volume, or Lebesgue measure, right? Euclidean volume. Okay, and this is related to some very, very degenerate case of transport, this lemma. And the second claim is that if I look at the level set lambda smaller than r, so its volume to 1 over n, so it should be at most r over n times, I think, Lk. Because the dual would, for r equals n, this is the dual body. And for the dual body times n, which should give you, yes, okay, times constant. Okay, so now so given 1 and 2, let's finish. How do we finish? So we remember that Lk is the determinant of the covariance of x. So now we assume, okay, so we assume that x is isotropic, but uniform x in Rn is isotropic. Uniform distributed in K. Okay, so now we argue as follows. So what is Lk? Lk in general is the determinant of the covariance of x over the volume squared of K to the power of 1 over 2n. But this is just 1. X is isotropic, so this would be the volume of K to minus 1 over n. So that's the isotropic constant. Okay. Now we know that by the first item here, since the power is negative, this is at most the volume of the ball of square root of r to minus 1 over n. And this ball contains the level set of r times 1/2, but the 1/2 is absorbed in so a smaller than b means A smaller than some constant times B. Okay, smaller than lambda times R, but this is larger than this thing here, so I'm going to get n over R Lk, which is, R is n over sigma, so it's sigma n square over Lk. And so Lk is smaller than n sigma square over Lk, which gives Lk is smaller than sigma n. Okay, so what is remains to be proven is those two bounds 1 and 2. Okay, these are very short proofs. So how do you prove 1? So for 1, I'll go as follows. So I know, look at the function f. You remember this function f, log determinant of the Hessian. Okay, I know that f of 0 is 0, and it's square root of n sigma n Lipschitz with respect to the metric G. Therefore, f is between smaller than n on the ball 0 of square root of n over sigma n, which is the ball of radius square root of r. Because it did not travel more than this distance. You are Lipschitz in this ball, so the product is n, so it's more than n, which means that the determinant of the Hessian of lambda is between e to the n and e to the minus n on this ball. Now let's look at the gradient map. So recall that the gradient of lambda of y is the expectation of xy, which always belongs to k. It is some distribution on the convex set k. What? No, say. Oh. Don't say nothing if there is a typo. Any more typos? Okay. So it means now let's do change of variables. So the volume of K is at least the volume of the image of this level set, because it's larger than the image of everything. Grad lambda is always inside, so it's larger than the image, which is the integral of the function 1 on this thing. And just do it to help me change variables. Say dx. And now if x is grad lambda y, I'm going to get the integral where lambda is smaller than r of this determinant, which is at most e to the minus n times the volume. So this finishes 1. Okay? Now I need to prove 2. So I'll prove 2. I'll just erase the statement of 1. I'll prove 2 here. Okay, so how do you prove 2? So let's recall this concept of a polar body, which we mentioned when we said Bourgain-Millman. So just note that if y is a point in RK polar, then it means that the Laplace transform at y is the log of the expectation of e to the xy. But x lies inside k all the time. So the scalar product between x and y is at most r. So this is at most r. In other words, R k polar is contained in the set where lambda is at most r. So the volume of this set is at least the volume of RK polar which by Bourgain-Millman, it moves C to the n. Ah, the ball. Yeah, always the ball. Yeah. Thank you. Always the ball, the ball, the ball. Yeah, thank you. Okay, and so this is at most C over n to the n by Bourgain-Millman times R to the n. Okay, maybe put 1 over n all the way, this is better. So this is at most R times C over n times the volume of K to minus 1 over n. And this is LK. So this is this equals CR over n times LK. Okay, so this proves this part. I was hoping to prove more things, but I have no time. Okay, but this is all. Any questions? What? Yeah, so there is yes, you're right. So there is something called sub sigma n, which is enough to bound. Sub sigma n indeed is you take the maximum of all x log isotropic. Of the expectation of x1, let's say, times x squared. Over n. So this is enough to bound this, which is smaller than sigma n squared. Is that what you want?
Yes.
Yeah, this is what, please.
You said that the list was like a reverse inclusion for when you reach n, or?
Yeah, I said that right. You're listening. Very good. Yes, so and indeed, yeah, that's an exercise. You can thanks, okay. Yeah, always. So the claim is that this thing is roughly nk polar. So this contains up to universal constant and is contained. So I had no time to elaborate, but yeah, I knew that this is tight. So scaling by R is easy. Yeah, but this is it's not an easy exercise. But it's not like okay. Yes. More questions? Yeah, I was told that you should never stand between an audience and their lunch, because otherwise you might become the lunch. But okay, so sorry for taking 10 minutes from your time, but it was the photo. So, okay. Thank you.